Okay. Are you able to see the screen?
Yes, sir.
Okay. Lecture 4. This chapter is talk about hydrostatic force. So far, what we learn? We learn. We start from fluid property, right? Then some law. Then we measure the pressure inside a fluid at a certain depth. Then just previous lecture, we learn about how you can measure the pressure, either using a manometer or either using a mechanical device, right? But we have a very good tool. Tool mean equation to measure the pressure at a certain depth of fluid. That pressure is H rho G equal to P, right? Or we can say P equal to gamma H. This is very good tool. Say if a dolphin swimming under the sea at a certain depth, okay, say depth is 500 meter, you can easily figure out how much will be pressure on his body, just top surface, right? Uh, and you can just sitting your decks and calculate the pressure. So pressure P equal to H rho G, you figure out. Similarly, pressure from the wall side will be same for static fluid, right? From this side will be same. Now, if I say instead of, or if I say the top projected area of the top surface of body of the dolphin is 0.08 meters square, then how much he will experience the force at the top surface? Or if I call that is a submarine at that depth, and just think this is the top surface is roof, kind of horizontal or flat. If I give you area, you can figure out the force, right? You figure out the pressure from the depth, then force equal to pressure into area, right? So you see a submarine at depth, you will feel pressure from this side, from this side, from all around, the pressure will be same magnitude, right? So a submarine kind of a tube. So if pressure is too much and body is not strong, then it will squeeze and ultimately break down and remain under water. And similarly, in case of dolphin, you see a lot of pressure, but still his muscle will carry all the pressure. Okay. So my intention is to explain the importance of the equation P equal to H rho G. Other thing that fluid pressure is very important things. If you are not calculate fluid pressure properly, you cannot design some structure which will be submerged in the water or floating in the water. For example, you cannot design a, a dam. Say you have a dam and this side has a water. So if you design that maximum water level in the front side will be this much height, then you see if I look from this side, then right over here, depth is 0. You gradually coming down, your depth gradually increasing, and right over here, pressure will be high because the vertical depth is high, right? So if you design a dam like that or canal on the canal or river, then the bottom has to be more wider because it will experience more pressure. This is one thing. Other thing, normally you'll see those dam. They keep some opening because if any region in the front side water is height is increasing, then it might be overflow or the dam might be damaged. So we have an option, then you can cut the dam little bit at certain location. For example, after 1 mile or 3 miles. And right over here, you can put a vertical plate and we attach some screw that is called switch gate. You can take it, you rotate the screw, it will open from the bottom. Okay, and water will pass under the plate. But it say your plate is close. Plate is close, then this plate, this is top, this is the bottom. So if water level, this level come right over here, your pressure, water pressure will be 0. Gradually going down, water pressure will be high. Now, how we'll figure out the total pressure force due to the pressure, how much will be the force? Because you see, you cannot take this reading because pressure is 0. Coming down, pressure gradually increase. So which value you will take? So if you know the pressure, then your force will be area into pressure, right? And you see pressure at top surface 0. So this plate, if I look from this side, then you see if this mass is thickness, then pressure on the plate right here is a high, gradually moving upward, pressure will be decreased, and finally say right over here is 0. Now then obviously you cannot take the bottom one or you cannot take the upper one. One option you have, you can take average, right? The which average you will take, top and bottom. How we can measure the bottom? But if you know the height, you can measure, right? But if you take multiple point, then your average, say you take 100 point, 1000 of point. Between this point to this point, then take average, then it might little bit close to the accurate result. But this is not the process. You have to mathematically prove that you can figure out a equation or formula to figure out the pressure. Okay. So you see the resultant of all the forces or pressure should work through a certain point, through this point, right? So if you able to figure out a formula to figure out this force or pressure working through this point, and if I know the location from the top, that at what height or depth the total pressure force is working, then you can design the gate properly, because you have to make sure that what will be thickness of this plate, what type of material you use, other thing in the both side, and also you have to make a support to strong enough that that support will carry the load, because pressure force ultimately work from right over here in the plate, right? So this plate, if you think other way, that this is a cantilever beam, this pressure working right, uh, let me take the arrow, right over here, you have support at the both side. So this is the support. Then you can figure out, if you know this force, if you know this force location from the, then from the geometry and from the location of this pressure, then you can figure out these two reaction force, this one and this one. Then you can design the switch gate. Similarly, you are working in a shipyard and design a bigger ship that will carry the cargo load from the oversea. So in that case, your say with load, this mass will be submerged in the water. Then how much will be force in the side of the ship due to the water pressure? If you not calculate, if your design is wrong, then due to the water pressure, this side might be breakdown. Okay. Sometime wave coming with higher speed and hitting the side of the ship, then it will break down. Okay. So there is a huge application of uh, figure out the pressure force of fluid in a parts or structure. So that's why the name of this chapter, hydrostatic force. Okay. So I just trying to give you a intro about the importance of this chapter. So let's go through this chapter. So it's saying you need to know certain term. Number one thing, total pressure or total pressure force and center of pressure. A body remain underwater, it will have two things. Say this is our Swiss gate plate. Number one thing, that it will have all the pressure, say from the right side is working, right? In the bottom, pressure will be higher, and in the top, pressure will be low. So resultant pressure will work through a point, for example, right over here. And also, there is a CG of the structure, center of gravity. So this might be at the center of the plate, right? Two things is there. So at first, we need to know what is total pressure. It's saying when a static Obviously, we are working with the static fluid, like static mass of fluid comes contact with a surface, either plane or curve, a force exerted by the fluid on the surface, either plane or curve. Okay, this force exerted on the surface, this force is called total pressure. Actually, I would say better to call it total pressure force. But in sometimes some book they mention as a total pressure. You taking shower from a bucket of water and you fill up the bucket with water. How the pressure force work at the bottom of the bucket and other thing. Pressure always work perpendicular to the surface. So they have inclined surface, your pressure working like that. Gradually it will decrease. You will move from the bottom to top. You coming down, then pressure increase. And at the bottom of the bucket, pressure will be uniform, right? Now, if you like to carry this bucket with full of, say, this much water, you like to carry the bucket by your hand. Then what we'll see, if your bucket material is thin or weak, then bottom will be deflected like that. That means there is a force working. So, for example, you buy a new bucket is okay, but bucket material is extremely thin. Sometimes, say, made of a plastic polythene sheet. Then you will see this side will be deep also deflect. If wall is strong enough, the pressure force working on the bucket from this direction, it will resist by the strength of the wall. Okay. So remember that when a structure or when a fluid comes contact to a structure, then it will apply some pressure or force perpendicular to the surface always. And this force is known as total pressure. And it's saying that it is always work in the direction normal to the surface. And point of application of total pressure on the surface is known as center of pressure. So all the resultant force where is working through a point. That point is called center of pressure. Right over here, you see a curved surface come contact a fluid or fluid come to a contact to a curved surface. So what will be happen? All the fluid pressure in every point is working. It will be perpendicular to the surface. And gradually you are moving upward, your pressure will decrease from the surface. At the top surface, it will be 0. So if this resultant, now how it will be balanced? By the strength of the wall. So your reaction force will work along this direction. That means wall will resist, right? All the force. Now, resultant of this force might work through a point, say this point. Now, location of this point is called center of pressure. Okay. It is needed to find the magnitude of total pressure and location of pressure center to design hydraulic structure. Hydraulic structure means those structure submerged under fluid or floating on the fluid. So right over here, what it is showing that resultant force is working through a point, through this point, and you can put a reaction right over here. For example, you submerge a sphere in the water, then all the pressure will work perpendicular to the surface. So all the point, that means it will work, direction will be toward the center of the sphere. Okay, and if this one is the water line, obviously right over here pressure will be low, this will be high, and gradually moving upward, it will pressure will decrease, depends on the size of the ball. Okay. Now, right over here, I am just showing a picture, and you see in the picture is showing a inclined surface, and this inclined surface, uh, this area is different, and this is the hash, and right in the black one is a plate, remain inclined in a dam surface. For example, if I draw, say this is a dam going like that. Okay. So just I described before that you can cut a portion of the dam, put a sluice gate for controlling the water flow. In that case, it will be vertical, right, along this location. But if you keep opening through a portion, and you can put a inclined plate over here, right? You can put a plate, and you can move this plate downward or upward to control the water flow. So you see this plate is not completely horizontal, it's angle with certain angle. If I make a line like that, that means making certain angle with the horizontal line, right? So this one is showing over here. So in that case, our plate is right only this mass. This mass is the plate. So if you have some mechanism, you can slide the plate upward, then gate will be open. Is pushed down, gate will be closed. But when water level will be this much, then you need to figure out how much will be force in the plate. Where is the resultant force working? Then you start to design what will be the thickness and what will be the material. Okay. So this is the inclined surface of the dam that I show you before. And this is the plate. And this plate, this much is inclined length along the dam surface. And this arbitrary shape is AB. This is A, this is B. So obviously it has a area of this plate. It has a location of CG that is showing over here. And also it has a pressure center. That means resultant pressure is working through a point, and it experiencing force and pressure. If we know the pressure, we can figure out the force. So you see, this is the top surface, free surface, and right, this is the bottom of the plate. Around inclined distance, we uh, make with denoted by y-axis, y, and the vertical depth we mention with h. So how we can figure out the total pressure? And this is the theta. Now, over here we have two axes. One is x-axis, other one is y-axis. So I need to show you that which one is the x-axis, which one is the y-axis. So this is my dam. So you say this point is over here, this point. So if you move downward the inclined surface, that means you are moving along y direction. And you move along the length of the dam, then this is x-axis. So in our case, x-axis is going to the screen, to the monitor. Okay. Now, how I can figure out the pressure force? Number one thing, this one we can apply sine theta, cos theta to convert the inclined distance into vertical distance. So in this plate, I am taking a very small segment of the plate. And this segment, the vertical inclined height is dy. I'm taking this area, small area. I'm saying this area is dA. Excuse me. An inclined surface from the top surface, inclined distance is y. So this is the y. So vertical depth is h, and there is a relationship because this angle theta, right? So if I make a triangle, this is my inclined distance y, and vertical distance is h. This is theta. Then we will get this done. That sine theta equal to h by y. Now this plate has a center of gravity, say right over here. And center of gravity will be at a inclined distance is y bar, vertical distance is bar. So these plate have a pressure. In the bottom it will be pressure more, you moving upward, pressure will be low. So all the resultant pressure work through a point. We thinking this is this one right over here. CP, location of CP. Now, I put CP, or they use CP, put bottom of CG, but it could be like that, that CG at the bottom, say right over here, and CP at the top, right? You might have a question why you are not keep considering like that. But actually, the center of pressure is always work bottom of center of gravity, and we can prove mathematically. Okay, so right over here, this one we are thinking, this one center of pressure, and we indicating distance yp, and vertical distance we don't mention it, we don't need it, but still you can figure out vertical distance will be, you can say hp. Okay. Okay, now, So this small strip is dy. Vertical height is h. You see, if I make vertical height, then right bottom we are saying h. What will be height over here? Less than h. But we are concerning the area extremely narrow, dy, small segment. So we are not considering that difference. Okay. So how much will be fluid pressure right over in that small segment? Fluid pressure we can figure out, right? P equal to rho g h, right? Or we can say gamma h. Now h we can put in terms of sine theta, right? If I in terms of distance y, then it will be gamma, you see h value right over here, gamma y sine theta. Okay, gamma y sine theta. This mass pressure will work in that right over here. So pressure working in the small area, how much? Force, how much? Force equal to pressure into area. So if I consider very small area, so force working in that area will be very small. So I can say force is dF. So dF equal to P into small area, or small area dA. Now that P, if we put it over here, we are getting gamma y sine theta dA, right? Now, how we can figure out the total force? Just integrate both sides, and integration will be over area. Now, you see the area of this small segment we are calling dA. This dA will depend on y, because if y is decreased, then this thickness will increase. So dy will be, I'm saying my y is from here to here, then dy will be this much. If y value is increased, di will be very small. That means if I integrate both sides, in the left hand side, I'll get f. Right hand side, gamma sine theta, I'm taking out front of integration. Then integrate y dA of area integration. From, if I express y dA by something, then I can get the amount of force. Okay. So let's see in the next slide, we figure out the force, that how we did it. Just you look. You see the pressure right over here is P. So P equal to gamma H, right? Gamma H. Then this H we express in terms of inclined distance, gamma y sine theta. Now area of the mole strip is dA. If we multiply by P, we are getting force. But that force for only in the small area. So we express it by dF. Now this P, we put this value. So gamma y sine theta dA. Now you do the integration on the both sides. So F equal to area of dF, and dF equal to this mass. So we put this mass over here, and gamma sine theta, you take front of the integration. Now, we need to figure out mathematically, we need to apply the knowledge from your engineering mechanics, that what is this value? Can I express this value by something else? So I can have a formula. If I say this value is equal to, this value is equal to alpha, then your force, what is coming? Force equal to gamma sine theta into, say, some constant alpha. You have the formula. Now, we need to understand what is the integration portion. YDA, what does it meaning of YDA? Right, this portion, this one actually you see integration on area. So this one I can express with this term. I can say y into area A1 plus y2 into area A2 plus y3 into area A3. Integration means summation. Then what about the segment that we can write down, right? So when you use this type of formula in engineering mechanics, you figure out calculate the CG of a body, multi-body or single body. And you use this kind of formula. You remember that, say, XCG equal to sum of area AI, sum of XI, I equal to 1 to n in the bottom, sum of area. Sum of area mean area of the whole object, right over here, total area. Then you take the summation. Do you remember? When did you figure out this one? Say, for example, you have a body, a rectangular body. Then you have a triangular. Now you have a hole right over here. And right over here, your horizontal and vertical axis. How will you figure out the location of CG of the structure? Say it might be right over here. How will you figure out? By this formula. Okay. So this formula, I can, in the top part, I can write down the integration of A into x dA. Integration of x dA. So similarly, y dA, we know that if you figure out a y CG of a structure or area that equal to, at the bottom, total area of the plate, that I was showing a plate with, it has some portion triangular and then rectangular, then also it has a hole. So in that cases, you have to figure out total summation. How summation? You can figure out area of the triangular portion, say A1. Then you need to figure out vertical height of the CG of the triangular portion, say Y1. Plus, you figure out the area of the rectangular portion, YCG of the rectangular portion. Now there is a hole. Hole, you know the radius, you can figure out the area. So minus area will be Y3 and Y distance. I can write down this way. We can figure out this one. And this area A equal to A1 plus A2 minus A3. If this is no hole, let's say we have triangular, then and also it have a like that, then this will be plus, and this area will be sum of this area, this one, this one. Okay, now this one I can express other way, that y bar instead of summation I can say by integration, y into dA divided by area. So that I put right over here. Now this YDA, we can figure out the YDA equal to Y bar into area. So they put it over here. O gamma sine theta into A Y bar. So a very simple thing. So now you see this is our total pressure force. Now I can express in terms of vertical height. Then it is coming y into y bar into sine theta equal to h bar. So formula F equal to gamma h bar A. Okay. So this equation state that total pressure force on any submerged plane surface is equal to the area and pressure working through the centroid of the body. You have to figure out how much pressure working at the center. Easily can, if you figure out the location of the center, H bar, then you just use this formula. If you know the theta, if you know the Y bar, you can figure out H bar. Okay. And what is the A? Area of the plate. If it's rectangular or circular or triangular, you can figure out the area. Now, what is left the other thing? Other thing we need to figure out what will be the location of center of pressure. So let's see how we can figure out. So far, any question? Anyone? Hello?
Sir.
No question?
No, sir.
Okay. Now, what we'll do, we'll figure out the location of center of pressure. So, what we thinking that pressure in the right over here, force will be high. Our pressure force over here low, gradually is moving inclined distance or vertical height, your force will be decreased. So resultant force must work through a point, right? So we are thinking that resultant force is working through this point. And this resultant force is F. Now, is not the force resultant pressure. We call center of pressure. How we can figure out their distance? So I can think this is my resultant force from the resultant pressure. We already figure out the force, right? But we need to figure out the location, location of resultant pressure force. So this point we consider the distance from the inclined surface is YP. Now, how we can figure out? You see, this is a static body. The body is not moving. If I take moment along x-axis right over here, then what will be the moment? Moment due to the F, and the moment due to the all the pressure force showing with the red color has to be equal. If not equal, then uh, the body will be rotated. You see, this resultant force actually is coming from the fluid. But as an engineer, how will protect it? That means you have to consider that this will be my reaction force from the support. If this is reaction force, then some support in the support, its force will be along this direction, right? But that means this force, you can think the some force going with the top support and also bottom support. Now, if this body is not rotating, then moment due to the force F and moment due to the all the force working in the small area has to be equal. Now, how will figure out the force? A moment, force into distance, right? So force working in the small area, how much? We figure out already previous DF, force working in the small area is DF, right? That DF we already figure out. I'm taking moment right over here for DF, that is working in the small segment. So what will be my moment? Force into distance. What is the distance? Y. So I can say Y into DF. And Y into DF, this is working on a very small area, moment, this segment. But I like to figure out the whole. Similarly, if you take right over here on segment, he is experiencing some force gradually all over the place, right? So if I take the summation of the all force, that means integration, that will be the total moment. Total moment if you consider the small segment. Now, what will be the if the resultant force is working through this point, what will be the moment? Resultant force is F. Again, force into distance. So this moment will be F into what is the distance? YP. And this 2 has to be equal. So we are getting F into YP, Y dF. Okay, this one. Right over here, it's saying distributed force can be replaced by a single resultant force working at the pressure center without altering any reaction or moment in the system. So that's we figure out that total moment will be F dF into Y, right? And instead of that moment, I'm thinking a resultant force is working F. What will be that moment? F into YP. And that's saying these two has to be equal. Now, from here, we are getting FYP, target to figure out the yp. So yp equal to ydf by f. You see this one. Now the value of f we already figure out from the previous slide that f is this much, and value of df also we figure out df is this much. Now we figure out the y into df divided by f, that value we figure out. So if this one you put in the bottom, this one you put in the top side. So top side y into df, right? So you see sine theta, this sine theta will be out. Then this gamma will be out. In the bottom, you will have a y bar. In the bottom, a y bar. In the top, there is a y right over here, and one more y right over here. So you get y square integration of dA. So you getting this one, y square dA. Now you think, what is y square dA from your engineering mechanics? Y square into area integration. What is this value? Anyone? This is moment of inertia. What is moment of inertia? By definition, moment of inertia mean moment of area, but you have to take twice. It's called double moment of area. How, say, you have a y-axis, you have a x-axis. Just thinking you have a small area is dA, and here's a CG right this point. So this location of CG, vertical distance is y and horizontal distance is x. Now you take moment of this area. I will take the moment. Force into distance equal to moment. Right now we have to take area into distance. So distance y into area. This you are getting the moment of area. I am saying dm dm. Right over I am putting area for on time. But moments of inertia is equal to double moment of area. That means you get one time moment. Now take it again. That means again you need to multiply by distance y. So this you are getting for small area dA. So moment, total moment of area along x-axis, you are ultimately getting y square dA in area integration if you have a bigger area, arbitrary area. This m, moment of area, double moment of area, is called moment of inertia. That means this equal to, ultimately you are getting y bar, moment of inertia along y-axis. Okay, I'm sorry, along x-axis, because x-axis distance is y. If you take this distance x, then it will be y. Okay, so ix. Did you remember this equation? Anyone? In engineering mechanics, you look your class note that ixx equal to y square dA integration, and iyy equal to x square dA. Okay. So this one, this value we know equal to Ix. So you just put over here. So Ix equal to A into Y bar, right? Now this Ix respect to what? CG right over here. We are taking respect to x-axis right over here. But your body is right over here. Now, how you can say, for example, you have x-axis, you have a body right over here. This is y, this is x. If this is height is h and width is b, then what will be inertia along x-axis? If CG is right over here, then it has also axis, that this vertical axis, this horizontal axis. So what will be value of ICG? ICG mean you taking inertia this point, this CG, not the axis. So I'm saying I bar x equal to how much? 1 by 12 b h cube, right? Similarly, IY will be how much? 1 by 12 H BQ, right? Anyone has any confusion right over here? These two inertia, you are getting respect to the CG of the structure. So you have rectangular right over here, respect to this point, you are getting inertia. This is location of your CD, and area of this plate is A. This vertical distance is D, and inertia along x-axis, I am saying I bar x. What will be inertia actually through this x-axis? Anyone? Which formula will apply? Parallel axis theorem. You remember in the engineering mechanics that inertia of a object from the x-axis equal to inertia of same object along x-axis respect to the CG of the body plus area into d square, a d square. This is called parallel axis theorem. So this ICG I can express with I naught. I'm saying I naught plus area into d square. So what is our d? Right over here is y bar, right? Right over here. D is the distance from CG to the axis. So our x-axis is right over here, going perpendicular to the screen. What is the distance of CG? Y bar. So A y bar whole square. Now, so Ix equal to this mass. This Ix, we'll put it over here. So if Ix, you put it over here, then the bottom we have Ay. So I naught by this value. Right over here, A will be out, only Y bar. So this is the location of center of pressure. So from the equation, which one is bigger? Yp or y bar? Anyone? This is my Yp, and this is my y bar. What is the y bar? Location of the CG, and yp location of pressure center. So you look in this area in the right side and tell me which one is bigger from the equation. We can mention from the equation you see uh, inertia cannot be zero, area cannot be zero, location of distance of CG cannot be zero. So this term have some value. If this is zero, then what will getting? You are getting yp equal to y bar. But this is cannot be zero. This is positive value. So always you see yp is greater than y bar. Okay. So that's what saying where I naught is the moment of inertia of the plane with respect to its own centroid. A is the area of the plane surface, and y is the distance between the centroid and x-axis. That means this is y bar. Okay. Any question from anyone? Any question? Okay. Mm. So we have two formula, you say. Number one formula you need to know that amount of force working in the body. That equation is this one. And if you have angle, value of angle, then you can, if vertical height is given, you can convert in inclined distance. If inclined distance is given, you can convert in vertical height by sine theta, applying sine theta, cos theta, if angle is given. So this is the F. Now, what is the value of location of pressure center? This YP equal to this one and this one. So what you look carefully, this is gamma. Gamma equal to rho g. You know fluid density, you get the gamma. A is vertical distance, A area, right? And right over here I naught and y bar. So you need to figure out the CG of the structure and inertia respect to I naught. For example, if I say a vertical plate right over here is not in a inclined position, even vertically submerged. This is the free water surface. So what will be the CG? Location of CG of the structure. I can say, for example, this is 6 feet and this is 5. So where is CG? This is 6 feet. Obviously, this will be at the middle, right? And this distance will be 3. From here to here will be 3. If you know the vertical distance, you can get the y bar. But the y bar will be this distance plus this distance. Area of the plate 5 into 6. Then I naught area along x-axis will be 1 by 12 b. B will be 5, h will be 6, h cube. Okay, easily you can figure out. So let's see we can solve a problem. Okay, other thing, this is engineering mechanics, it's not engineering mechanics class, right? This is fluid mechanics class. I think engineering mechanics class, you already did this kind of stuff, Like you have a multiple area, some portion is square, then you have a rectangular portion, then you might have a triangular hole right over here, and you might have a axis over here. Now you figure out the location of CG, figure out the moment of inertia. You did this kinds of problem. So if this type of plate is submerged in the bottom of water, say you have a hole also over here, how will you figure out the force? So in that case, you need to figure out the location of the all CG, right? Also, you need to figure out the moment of inertia of the whole body, the whole plate. So how we can do it? So in that case, you don't have to start like from the engineering mechanics, but if I give you this type of problem, I have to give you attached a formula sheet with the question. For example, so you can easily figure out the value of I naught location of the CG from the formula sheet. For example, if I give you a rectangular plate right over here, a rectangular plate, if I make a figure over here, bigger arm length is B right over here. It's calling B, and height of the triangle is H. So you can figure out the area from the formula half BH. Then this length is C. Then you can figure out the location of XCG from here along this direction. This CG right over here. X bar, if I magnify, this is X bar right over here, X bar. From this corner, X bar. X bar equal to B plus C divided by 3. And Y bar equal to H by 3. What will be inertia? Right over here, this is inertia. So easily you can figure out. Similarly, if a circular plate I give you, this is the area, and YCG, XCG, this is the formula, inertia is this one, okay? Similarly, if I give you a area that is semicircle and remain underwater, so how will figure out the YCG first? So you let me draw a sketch. Say right over here, this is free surface, and under water, right over here, a half circle plate in the remain underwater, and vertical height of the top is given, top surface. Now, what will be the y distance, uh, y bar? Y bar will be distance of the CG. So say CG right over here. So your y bar will be distance from here to all the way right over here. Now, how will you figure out this distance? That what is the location of the CG? So y bar, if I say this is H, vertical depth, and this one, if I say only y, YCG, that means coordinate of CG from the top surface. Then your y bar in the formula, that will be equal to H plus YCG. You need to add this term. Just mention one thing, you need the distance of CG from the top surface. That is the main thing. Now, in the formula, we need area. We need to know inclined angle. We need to know I naught, and we need to know y bar. So area right over here. Now y bar value, you see from the top flat surface is y. This is this one. So this YCG actually this value. And I naught you get out from here. I naught equal to this much. So it's very easy. Similarly, if I give you a elliptical surface, right over here is the formula. Okay. Now, so far, any question? Anyone? No question? Hello? Okay, we can continue. So you see, it's this problem is saying a vertical trapezoidal gate with its upper edge located below the free surface of water is shown below. Determine the total pressure force and center of pressure on the gate. Now, how we can figure out? But you see, in this problem, theta value is not given, but it's saying one things mentioned over here, that is a vertical trapezoidal gate. So what does it mean? This one, our inner derivation, this one our inclined surface, right? And right over here, there was free surface of the water, and this angle was theta. So when this inclined surface become vertical, if theta value decreasing, that means it become like that. Your dam become more wider, right? But if theta value gradually increase, then how it is look like? Then your dam will be narrow. And increase more, gradually this wall will be vertical if theta equal to 90 degree. So this plate, not the inclined surface, is remain at the vertical position. So that's why in this case, although theta is not given, but theta will be 90 degree. Now, what is our formula? We need to use two formula. One is force, other one is location of center of pressure. So force formula is this one. In that case, gamma we know 1000 kg per meter cube into 9.81, or gamma equal to rho g. Theta is 90 degree and sine 90 equal to 1. So which value you needed now? We need the y bar or h bar. So what is the relationship between y bar and h bar? We show it that this is the triangle. This angle is theta. This is theta. So this is y and vertical height is h. So if I say this is y bar, sine theta equal to h bar divided by y bar. Okay. So if you know the y bar, then you can figure out the force. Now, how will you figure out the y bar? Now, in that case, y bar and h bar is same. Now, say CG around right over here is working. So your y bar will be the vertical distance from the top surface to the location of the CG. So what is the vertical distance? This mass is 5, but this value we don't know, like this mass from here to here, right? If we know this distance, then we can figure out the y bar. Y bar will be equal to 5 plus this distance. Now, uh, how will figure out the center of pressure? Yp equal to I naught area of the plate into y bar plus y bar. So you see, without calculating y bar, you cannot do anything. Y bar, I naught, and location of CG is very important. Now, how we can figure out this y bar? If you look in the formula sheet, that if a surface is trapezoidal, then what is the value of area? H into AB. H into AB, you look carefully, this is equal to H is the height, and A and B length of the arm, bigger and smaller arm. Y bar, Y bar equal to, this is the formula. And you look for me, Y bar there, this is Y bar. That means Y bar is the distance of CG from the bigger end. Okay. And right over here, this is the I naught. Now, you have to be careful about choosing A and B. Remember, B is the bigger end length, A is the smaller end length. But if you think this is A, this is B, over here you are still okay. But over here, your result will be wrong, over here will be wrong. That means your problem has to be matched with this formula. So you have to be little bit careful. Okay. So in that problem, okay. So this problem, we need to figure out the location of the CG by using formula. So let's see how we can solve it. At first, you will say given. What is given? Depth of the top surface is 5 meter. Is given over here. That is mentioned over here. Density of fluid, water, on 1000 kg meter cube. Then in the formula, A is the smaller length, A equal to 1 meter. You say the geometry of the trapezoidal plate, smaller arm length A equal to 1 meter, bigger arm length B equal to 3 meter. Height of the plate is 2 meter. What you need to figure out? Hydrostatic pressure force, and also you need to figure out location of center of pressure. Now, at first, by using the formula, you figure out the area. You need area, you need I naught, you need to figure out Y bar. So at first, you figure out area from the formula. This is the formula. Then figure out the YCG. YCG mean in the formula, this is not Y bar. These are saying YCG. That means this is equal to only this distance. And which one is Y bar? Y bar is distance from here to here. So if you know this one, plus 5 will be Y bar. So you figure out the YCG 0.83. That means this distance is 0.83. Then I naught equal to this one. Then we have found I naught equal to 1.22 meter to the power 4. and H bar equal to H depth plus this YCG. That means this 5 meter plus 0.83 meter, we're getting 5.83. Okay. Now we need to figure out the center of pressure, YP. So right over here, we just get the height, right? Depth of center of gravity, Y bar. This is Y bar or H bar, same thing because over here your angle is 90. So H bar equal to Y bar sine theta. So both are same. I not, you know. Now figure out the force. This is the formula. Force equal to gamma sine theta area into Y bar. Y bar value we already figure out. Y bar equal to we found H bar, right? If theta equal to 90, then this and this one is same. So you just put over here. And we got 229 kilonewton force working in the plate. Now center of pressure, this is the formula, plus Y bar. Y bar 5.83. I not we figure out with the formula. We have the area of the plate and we have the Y bar over here. Finally, we got 5.88. So you see, this is location of YCG, and this is location of your center of pressure. Okay. So you see, center of pressure distance is higher. That means always below the object. So your center of pressure right over here. Now, if you like to support this plate in the top and bottom, which one has to be stronger? Bottom has to be stronger because your force, resultant force, is working through this point, which is close to the bottom S. Okay. So far, any question? Anyone? No? Okay. We can solve one more problem. Then we'll keep it off. Okay. So you see in the figure, it's saying an inverted semicircular gate. Inverted means upside down. You can put this two way. You can put flat surface at the top this way, or you can put flat surface element at the bottom in underwater. So it's saying an inverted semicircular gate shown below is installed at angle 45 degree right over here with respect to the free surface, this free surface. So immediately this is theta. Top gate is 6 meter. Top of the gate, it's saying 6 meter below the water surface in vertical direction. That means this direction is 6 meter. So that means from here to here is 6 meter. Determine the hydrostatic force. You have to figure out the F and you need to figure out the YP on the gate. So if this one is CG, this is YP. So you need to figure out YP and how much is force working. Remember, force always work through center of pressure, not through the CG. Okay. So let's see how we can solve it. It's very easy. We need to take the formula from the uh, formula sheet. And you see, if we know the location of C is vertical this distance, then your H bar H bar will be this 6 plus this distance. If distance is y1, then this will be 6 meter plus y1. Then you apply sine cos, you can figure out this y bar. Okay. So let's see if we can solve it easily. So right over here, we have two formulas. Just mention formula over here. We need to use this one. What this one? Same thing. Uh, and we need to figure out the YP from this. Uh, Hello, you need to turn off your mic. Okay, unmute your mic. Okay, so this is YP. This is the formula. Now you write down over here. Given. You see in the problem, the radius of this plate is given. There is a radius R equal to 4 meter, theta 45 degree, and height of the water is given 6 meter. Density of water, this mass. You need to figure out hydrostatic pressure force, F or P equal to how much, and also center of pressure. Now, at first, you need to figure out the area. So, how will, and this is the formula for YCG, right? This is formula from I naught. Now, you don't need to memorize this formula. If it is very simple, say if I say only rectangular type structure, then I might not give you the formula sheet. If area is circular, I'll not give you because it's easy to you can figure out. But if his area is like that is complex, then we'll give you this formula sheet. So in that formula sheet, what is our area? Semicircle, right over here. We need to use this one. So you see location of CG from the plot S is given. Y bar is this mass. I naught, you can use this formula. Area half pi r square. So you need to careful. In our case, uh, our is upside down. That means flat surface and remain at the top. So if right over here is CG, so we need to have this distance. We need to calculate from here to here, and this distance will be this value. So you see they are giving from the flat edge, not from the bottom. Okay. Okay. So we need to calculate all the parameter. First, you figure out the area. This one area. YCG 4R by 3 pi. What is R? Radius of the plate. 4 meter. You already got it. So you got 1.73. What does it mean? That means this distance, this one from here to here, this is 1.7. So what will be your HP? HP will be, I'm sorry, H bar. H bar will be distance from here to here. That means this 6 plus 1.7. So is H bar equal to H, vertical height is 6 plus YCG. That means 7.7 meter. Then we need to figure out the I naught by this formula. You got the I naught. Then H bar you have. Now how we can get the Y bar? You see, you figure out this is the location of CG. So you already figure out this height equal to 7.7. Now how we can figure out the Y bar from here, inclined distance? Just you use the sine theta, right? So sine theta equal to H bar by Y bar. H bar you got vertical depth. So Y bar is coming 10.88 meter, right out here. Now you have the wall data, you already have it, just you need to put there. So let's see. Pressure force, gamma, Y bar, sine theta, area. Area you already found. Sine theta, এখানে y bar into sine theta equal to h bar, or you can keep it, you can use the y bar, the same thing. So after reporting all the value, this you are getting result this one, okay? And it's better if you put all the unit, kg, meter cube, density, rho g h bar, g meter per second square. Then you can put h bar. Your h bar is meter, area meter square. Then you see this meter cube. This that mean he has a meter square, this one, and this meter will be take it out. So you will have only kg meter second square, kg meter second square. So kg meter second square, this equal to Newton. This equal to Newton. So you get Newton. Then divided by the 1000, you get kilonewton. Center of pressure using the formula. So we are getting 10.98. So again, you see your Y bar is 10.88 by pressure center, bottom of the Y bar, 10.98. So far, any question? Any question? Anyone? No? Hello?
Ji sir.
No question?
No sir.
Okay. Our time is almost over, so we'll leave it here. And if you have any question, still you can
Sir,
keep
sir, if
touch
you
with me.
please provide us a lecture 3 and 4, it will be better for our study.
Yeah, I'll put it today. Okay. 3 is
Okay, sir.
already
Thank you.
there, right?